Thanks. I would like to thank Steven Maenhout, who is a contributor of UCLEX. So he will be given 3 presentations today.
Only 3. Yes.
Only 3 presentations. And so the first one will be on breeding data management in Brno. So Steven Maenhout is a general manager of a Brno company. And I think so it's a small company which finds its origin in the long-term scientific symbiosis between the Department of Plant Production and the Department of Applied Mathematics, Bioinformatics and Process Control of Ghent University in Belgium. So Steven Maenhout performed his PhD research on the statistical and computational aspects of genomic selection in hybrid maize. Having worked several years as a commercial software and database developer prior to his PhD study, Steven dedicated recent years to implement the Brno computing engine in practical breeding, whilst supervising the development of the user interface of the software with involvement of large number of private companies, private breeding companies in the design and validation of Brno software. He is involved in UCLEX as a specialist for Brno software, which represents main database in the UCLEX project. So the first presentation, and then tomorrow, this evening, we will have 2 other presentations. Thanks.
Okay, thank you, Bernadette, for the nice introduction. First of all, I should apologize. I have changed the title a little bit, and I didn't inform the organizers because then they would be obliged to reprint all flyers and so the presentation is now called. The content is nearly the same. It's data-driven breeding: the way forward. It should be a little bit more nice. Secondly, I'm using a Linux station. So I can't use the fancy pointer that we saw yesterday, because that doesn't work. And thirdly, I did not use the template that was provided by Bernadette. So that's all for the bad news. Things can only get better from here. I would like to start with a figure that I'm imagining most, if not all of you, have already seen. It's the biggest showcase of plant breeding, the biggest success story, where all dairy cattle breeders show the milk increased over the years. Plant breeders generally refer to this figure where you see the increase in average corn production in kilograms per hectare over the years. So we see that initially, when the figure starts in 1865, there's little to no progress whatsoever. Then around 1903, but the actual application started in 1930, we see the introduction of hybrids, initially it weren't double crosses, but then double crosses, and we see going to single crosses that we get an incredible increase in yield, in the genetic potential. So this is not only breeding, it's breeding plus cultural practices, of course, though it's also nitrogen, fertilization, and so on. So this is not only plant breeders that can put this on their record. But anyhow, you see an incredible rate of genetic progress, which I guess is very hard to compete with within other species. Now, so it shows here U.S. corn yields have increased a 6.5-fold times in 75 years. So that's quite an accomplishment. And what is even more astonishing, in my experience, is that most of this progress, especially in the early years, has been realized with mostly visual scoring and very limited data recording. So limited data recording meaning paper and pen, people making decisions just on trial results where they made visual scores, and a limited use of statistics and quantitative genetics. So this is a bit of a contradiction to the remainder of my talk, where I'll be advocating use of statistics and quantitative genetics. But just to show that the low-hanging fruit, meaning a certain rate of genetic progress, can be obtained without going to these advanced methods. Of course, when you're at, I'll call it the current top of the genetic performance chart, I think it'll be very hard to improve from here on without using quantitative genetic statistics and what I'll refer to as data-driven breeding methods. So, what I'm hoping to do with this presentation is to try to convince you that the current, what is being adopted in most breeding programs today is the methodology of cross the best and hope for the best. Meaning you try to identify the best individuals in your breeding pool and cross them and hope that you will get offspring that is better than where you started with. Now that has worked, obviously, and that still works, but there are better ways. So that is what I'm hoping to convince you of. So I think most of this is already explained, but just because I'm advocating the use of quantitative genetics, it's quite important to realize that this is not something new. It's actually rather old. As you see, Mendel was slightly earlier, and then from 1900 you see Wilhelm Johannsen, who noticed that it's not only genetics, but there's both environment and genetic factors, which seems very trivial now. And Nilsson Ehle, who went beyond the observations of Mendel and noticed that if you have more than one gene causing a trait, in this case it's the color of wheat grains, and it's a very trivial case because both genes, the R and the C, have the exact same effect on color intensity. But if you have two genes that regulate a trait, and you make the traditional cross between two homozygous individuals, and you create the F1, create an F2 population, you get a kind of different, it's not the traditional Mendelian distribution in phenotypes, but if you chart these, I hope most of you will already start recognizing the typical Gaussian distribution, which is the foundation of most of quantitative genetics analysis tools. So if you go one step further, and so this is what we had here, we had 2 gene pairs. If you extend this to 3 gene pairs, 4, 5, you see a more continuous distribution appearing. Now, it turns out that this, what I'll call as a synonym for quantitative trait, multi-gene concept is the mode of inheritance for the majority of animal, plant, and human traits. Not all molecular biologists will agree with this statement, so please don't throw things at me. And the idea is that in quantitative inheritance, the segregation of allelic pairs at a number of different loci, and this is very important, each having a small effect on the overall phenotype. That's a very crucial thing, the last part, that one single gene in this distribution, one single locus, generally has a very small effect. And that will come back several times during the presentation. Now, I've already mentioned the Gaussian distribution being more or less the foundation of most quantitative analysis tools. So I guess most of you have seen this somewhere in a statistical course appearing somewhere. You get this typical clock distribution. And why is it so useful? Because it's this entire distribution, this entire graph, can be charted with only 2 parameters, being the mean, so the center of the graph, and the variance, being the width of the graph. So only 2 numbers allow you to describe, for example, the phenotypic distribution of a certain trait. You only need 2 numbers. So that makes it easy, or easier, to make predictions and so on, because you only need 2 parameters, either to predict those parameters or feed them as input to certain analysis methods. So it allows for a lot of simplifying assumptions during most, if not all, analysis techniques. I wasn't here yesterday morning, but I assume that this has already been presented, the response to selection. And this goes back to the statement, cross the best and hope for the best. So the idea here, I'm assuming this has been explained, you take the top, like in this example, 10% of your distribution, the top performers, you allow them to intermate, let's say randomly, and you look at the distribution of the offspring, and if you compare the mean of this distribution, the distribution of offspring, versus the mean of the population which you selected, you see that you're not reaching the same level. So unfortunately, we are not able to maintain our selection differential. We get a certain type of efficiency loss, and this is what is called the heritability of the trait. Basically, how much can we keep, how much can we maintain from the variance that we see here, how much is restored in the following generation. So heritability for a trait is hugely important. For a breeder, for example, if you're working on a trait that has very low heritability, it means you will have to do an incredible effort to make any sort of progress, because you can select the best guys here, next generation you'll just wind up right back here. So it often surprises me that companies that are contacting me because they are looking into, let's say, genomic selection and so on. So first thing I always ask is, what is the heritability of your most important commercial traits? And the answer I, in almost every case, get is, I don't know. So if you don't know what your heritability is, then how would you ever know that you're improving? You could get a very fancy method, genomic selection with artificial intelligence and drones put into the mix, and you've done everything right, but how would you know that this has added something to your current selection progress? So heritability and rate of genetic progress are your quantifiers to get an idea how much you're advancing by implementing a certain technology, or even just the way you're selecting these top 10% performers, for example. Just by doing more replicates in your trial or using different environments to do the testing of these individuals, you're already increasing heritability. So it doesn't have to be a new selection method. Now, what goes for heritability goes for rate of genetic progress. What you're seeing here is a typical graph I make for breeding programs to get an idea how well they are selecting. So first of all, if you don't have this graph and I ask is this trait, how is it responding, I usually get it works pretty well. We get new varieties each year, so we must be doing something right. Hard to argue against that, right? So what you're seeing here is I calculate breeding values. We'll get back to that part, the definition of that, but I calculate breeding values for every individual in the breeding pool and set these out like 2007 is the first year of introduction of these, so each dot is a member of the breeding pool, let's say a candidate variety or a candidate parental line or whatever, and this is their first year that they are being tested. So all of these have been tested in 2007. And you see there's quite a bit of distribution in genetic potential here. You got, let's say that this is a trait, let's call it yield, where bigger is better, right? So all of these guys, these would be your losers where you're not interested in. And the guys that are here would be your winners, which you would select to go to the either next round of selection or for commercialization. So what breeders do is try to identify those guys here which have the biggest breeding value, that are the most high potential. And as you can see, imagine that you're not doing any selection at all. Each year you will find some guys that just pop out. Normally, you could have bad years, you could be unlucky, but normally you can still find the top, let's say 5 or 10% performers. On the other hand, the idea of breeding and selection is to improve your breeding pool. So what you're hoping for is that by selection, your breeding pool as a whole is going up the scale, is having a better genetic potential for yield, for example. So you select, there are various ways, doing negative selection to genomic selection. The approach itself is irrelevant here, but the idea is that the average of the population, and it's the black line that you're seeing is a regression line, not to the average, but to the median of the population. So 50% of the individuals from that year are above the line and 50% are below the line. The idea is that you get a steady rate of progress for the trait by selection. And what you're seeing is the blue line is a kind of what is called a Loess regression. Less important, but it's not a straight line. It tries to follow more naturally the trend. And what you're seeing is that some years you're ahead, you're slightly selecting better, so other years you're behind, like this. But the general trend is very much increasing for the median of the population. Now the slope of this black line is basically an estimate of your rate of genetic progress. Big slopes means you're advancing really quickly. And if you have a flat line, it means you're not advancing at all. And then going back to the argument, yes, but we're still releasing varieties each year. That is obviously true. So I'll take the next graph. This is one where genetic progress is not that clear. So there is a small rising trend. If you look at it, it's 0.081 per year, whatever unit that you're expressing your trait in. So basically a flat line. And as you can see, it goes up and down. So, but each year, by just selecting the top performers, you're getting somewhere, right? So it's not that you have to, by definition, have a good genetic rate of progress to have a new commercial variety. The thing is, however, imagine that your competitor has this line. So each year, the entire breeding stock of your competitor is way up there, and you're still right here. That means you will have to make a lot more offspring just to find that top guy here, while your competitor has to make far less offspring because the median of his population is already here. So the advantage of increasing the rate of genetic progress is mainly to get more favorable odds of finding that top performing individual or individuals. And that's what is breeding should all be about. If you implement a new methodology, generally what I advise is look after a few years, what is now our current rate of progress, what was it before, and what is it now? If it stays the same, you probably wasted a lot of time and effort. So every new technology, how simple it can be from just adding a replication, adding a new trial station, towards implementing genomic selection on digital imaging, on traits that arrive from digital imaging, it is my opinion that you should quantify how much that brings to your breeding pool. And the rate of genetic progress is one of those. Now, what I haven't mentioned so far are the red lines here. The red lines are the regression over, in this case, the 5% percentile, basically the 5% worst performers each year, and the 5% top performers each year. And so you see similar lines, but what I also hope that you see that increasing the rate of the losers is quite easy. Just by removing them, you'll increase the potential of the really bad guys. Improving the rate of the winners is a whole lot more difficult. So the rate of genetic progress expressed over the median of the population is a parameter to quantify your success or your rate of genetic progress, but more interesting is the rate of genetic progress of your, for example, 10% top performers, which is a lot more hard. If we look at the second case again, you see that in this case, they're even going down. It's very small, very negative, because it's a whole lot more difficult to improve the top performers than it is to improve the median of your population. Now, I guess this is something that is also very known, and this is a law from economics, the law of diminishing return or marginal returns, and basically states that So this is expressed as a kind of implementation of a new technology. Again, technology could mean anything from we're going to use new trial designs, we're not going to use randomized complete block designs anymore, but we're going to use alpha designs, for example. That would be a new technology. So you implement it, and that is costing you effort to do, because you have to change your way of working. And then you would hopefully get a perceived performance, a certain return value of your investment, of your efforts. But at a certain moment, you will reach what is called the plateau level. Basically, that way you've exhausted that way of advancing. There are different ways of how you could interpret this. You could say, for example, we've gone, if we go back here, for example, we cannot increase the rate of genetic progress anymore. So elite maize varieties, for example, are in that case. It's very difficult to increase their performance just by improving some trialing mechanisms. You could also interpret this plateau, for example, that once all of your competitors are right there doing exactly the same, you don't have any advantage of your technology. Well, at least you can call it an advantage. It's a status quo. Everybody's doing the same. So the introduction of a new technology will always follow this kind of distribution. And the same can be told then for example, genomic prediction, genomic selection. It's not a magical method. It will require additional effort. It will require change, investment. You will undoubtedly, if you perform it well, get an increase in your performance, in your return value. But again, it is very likely that you will reach the plateau of that form of technology. Now, an often heard statement today is that we're living in the age of data. I completely agree with that. We have specialized software for data recording, for data analysis. We have the ability to use advanced statistics, decision support systems. There have been massive developments in genomic sequencing, SNP-chip, GBS. We've heard all of that yesterday. Genomic selection is one of those, GWAS, and you have sensoring, Internet of Things, envirotyping, if you know the term. That is where you actually monitor your entire your trialing environment. You're going to look at soil conditions, weather conditions. You will take every possible parameter that describes your environment and take that into account while modeling your data. So that is a term like genotyping, phenotyping, envirotyping. It's not really catching on, but I still put it here. High throughput phenotyping, drone imaging, and going on to artificial intelligence and machine learning and so on. These are all methods that rely on data availability, and the ability to process this data. Now, the problem with, if you look at this list here, I can imagine that for breeders or breeding companies or institute, that you often see that these are like distinct departments. You have the guys that are doing the genomics part, doing it really well. I'm always very much amazed. You have the guys that do the statistics. You have the guys that do the sensors, and then you have the phenotyping guys doing machine learning and image analysis. All very impressive, but in the end of the day, it's up to the breeder to use the outcome of all of this in a selection decision. Will I cross A with B, or will I cross A with C? Will I keep on this variety, or will I keep on the other? So how do you harness all of this data into a decision mechanism? Now, for that, again, going back into time, if you look at the breeding technology timeline, starting out with what I've already mentioned, Johansson's formula, where its phenotype is genotype plus environment. You go to the 1930s, 1940s, where you have the basic principles of quantitative breeding. Basically, the idea of breeding values versus genetic values, breeding values versus per se performance of an individual. And then things have been built on top of that. The entire blob mix model, which has been mentioned several times during talks yesterday, were basically created to make use of these basic quantitative principles. Animal breeding companies and institutes have been using these recording systems for the goal of breeding value estimation. So still relying on these principles of the 1930s, 1940s. QTL mapping, well, I cannot claim that they're using the principles, the quantitative genetic principles, but then it was kind of re-established with GWAS and genomic prediction in 2000, 2010, depending where you put the cut there. But my claim is that most of these data-driven methods that I've mentioned in the slide before can be harnessed still with the basic principle of quantitative genetics. So the basic principle of breeding value estimation, and this might sound very straightforward, is that you select parents based on the performance of their offspring and not their own performance. Now, I know that there are lots of forage breeders in the room, and they usually already do this kind of thing. They do these half-SIP crosses, test the offspring, and then you set the parents together. But the idea is that you cannot necessarily see the potential of an individual just by looking at its own performance. That is the entire idea, the 1930, 1940 basic idea. And this can go two ways, meaning you can have an exceptional individual in your breeding pool that performs astonishingly well, becomes a great commercial variety, but is not able to pass this on to its offspring. These cases exist. There's usually quite a high correlation between per se performance and offspring performance, but in some cases that correlation is very small. It depends again on heritability. And like the cartoon is showing, you also have the inverse, where you have parents which have their own performance is quite mediocre on intellectual level apparently, but have an offspring that performs really well. So the key message is here that breeding value estimation, data-driven methods, the idea is to find the good progenitors, the good parents. They might not perform very well themselves, but they might give good offspring. So that's the switch you'll have to make. So where does this come from? This is again the very basic formula of Johansen, where it says phenotype is genotype plus environment. So that is on page 1, or page 2 of every introductory course on genetics. On page 3, you then, of a quantitative genetics course then, you'll find that the genetic part is a bit artificially separated in two components. What is called the additive component, easily described by A, and the non-additive component, less obviously called the D part. It's called D because one of the theories is that it's caused by dominance, by heterozygosity, but hybrid breeders call this heterosis. Animal breeders or pig breeders call this the permanent environment. So it has different names, but basically the idea is this is the part that you receive from your parents, from their breeding potential, the additive part, and this is like the completely random part which nobody at this point can explain. It's like you have if there wouldn't be a D part, we would all be exactly the same height as our brothers and sisters. Height is a very heritable trait. Nevertheless, you see deviations that is caused by the D part. Now there are many theories on what is caused, especially in hybrid breeding where they call this a specific combining ability or heterosis. There are many theories. There's some say it's due to dominance, heterozygosity, epistasis, so interactions between genes. You have many articles proving one theory and then as many articles disproving the other theory. So there's currently, to my knowledge, no definitive theory that explains this part. But on the other hand, the additive part works really well. So what most plant breeders are doing, either completely aware of it or completely unconsciously, they are selecting for additive effects. So the idea is that the additive part is basically the part that you receive from your parents. So this is paternal, so it's basically the average of the additive part of the father and the mother of the individual. So it's, as you can see, in terms of equations, it couldn't be more straightforward than this, right? The only part that you have to realize that this additive part, the breeding value of an individual, cannot be directly observed from the phenotype, because there are two nuisance factors, two confounding parameters, one being the environment. Change the environment and you will change the phenotype. And secondly, the dominance deviation, the non-additive part, which makes it hard to see the additive or the breeding value of an individual from its phenotype. So the question is now, how do we do that then? Because it's all nice in theory, of course, that you say you have to look at the breeding value. Well, oh yeah, this is the part where I show what you can actually do with once you have the breeding value, so apparently going ahead a bit. But imagine that you have two crosses, two potential, let's say, parent A crossed with parent B, or parent C crossed with parent D. One being the offspring. If you would make many offspring of both crosses, you'd get this Gaussian distribution, right? And you have two crosses, and they differ in variance. So the red offspring distribution has a wider phenotypic variance, and you have the green one. Now, and there's also a difference in the mean of these populations. Now, if you're looking for, let's say again, that the trait that we're looking at is the bigger the better, so let's like yield, you would obviously choose the green population. So you would be making the cross, I don't know what I said, but let's say C times D would then be the parental cross. So one of the shortcomings of this approach is that with this breeding value estimation, so imagine that we have breeding values for all parents, for all fathers and all mothers, we can predict the mean of the offspring population. But what we cannot do is predict the variance of the population. And that is a bit unfortunate, because if I succeed at convincing a breeder to take this approach, and we do the math, we do these simplified calculations, and we then eventually say, you have to take the green cross. And the breeder says, okay, I'll believe you for now. I'll make the cross, and he makes like one offspring, just to validate if what I'm saying is even remotely correct. Now at that point, it's really a matter of luck if the offspring will end up here or will end up here, right? So I have a 50% chance of ending after the mean of the population, but there is an equal probability that I will have a very bad individual. So the idea is that quantitative selection like this based on breeding value is not something that is constant. I cannot promise that if you cross A with B or the green cross, that you will get the superior offspring. You just have the most likely, you had the highest chance of receiving those offspring. If you take the red cross, you also have a probability of getting a very good performing individual, but the probability is slightly lower. So basically, if you see breeding, I don't know if you see it that way, but if you see it as a sort of gambling, and you have to put your money on one of the two crosses, I would put my money on the green cross. So that is the way of reasoning. You cannot validate it afterwards by making one or two offspring and say, look, they were all bad, so your theory doesn't work. One, it's not my theory. Two, it's a probability, it's the laws of probability. Now, who is using this? Because, like I said, it is not really like I came up with it. So the theory itself comes from the 1930s, 1940s. The actual way of efficiently calculating breeding values over large breeding pools, we're looking at 1950s to 1970s. And the actual first applications, I think we can say late 70s and 80s for animal breeders. And surprisingly, also one of the very early adopters are the forest or the tree breeders in general. Which seems odd, maybe, but actually makes perfect sense because these people generally face very long generation cycles. So if they decide to go with the green or the red cross, it's very important that they make the most logical decision at that point, the most probable one, because it'll take them a few years to find out if it was the good decision or not. So for forestry breeders, there was also a very rapid adoption of these methodologies. And then it took about until the 90s for large field crops like maize, wheat, and rice and canola. And I think we can state now that for the larger companies are all using some form of, maybe they call it the general combining ability, maybe they call it the breeding value. Terminology may differ, but the approach, the ideas, is completely fixed as the standard selection methodology. And then, depending on which company you're looking at, from the 2000s, you see vegetable breeders, potato breeders, and now also ornamental breeders. And when does this transfer happen? If you remember the plateau thing I've shown you, the law of diminishing return, as soon as they notice, by just each year crossing the best and hoping for the best, that is not really working out anymore. Or they see their competitors all of a sudden going much faster, having higher rates of genetic progress. At that point, you see that the adoption of breeding values becomes important. Now, this is the question I get most when I give this story, and people are slowly trying are thinking about if they are going to use this idea or not. The question I get is, well, okay, just show me how I can calculate this breeding value, and I'll do it, and I'll let you know if it's working out for me or not. So I get a lot of questions. Could you give me the formula for calculating the breeding value? Like we have the equation for for an analysis of variance or for calculating a mean or a median. Could you give me the equation for a breeding value estimation, and we'll be done with it? Unfortunately, it's not that easy. So first of all, if you have one plant, let's say one individual of your breeding pool, and you have put it in field trials, you've made observations for all the traits that you're interested in, at that point, you have no possible way of calculating a breeding value. Despite the fact that you might have put this one in 20 trials with multiple replications, the individual itself does not allow you to separate phenotype or genetic part, the additive from the non-additive part. So what you also need is field observations on the parental individuals. So at that point, imagine that you have phenotypes for the female and the male parent, and you have field observations on the offspring. Now at that point, you have a way of calculating what is the correlation between these observations that we're seeing here, and that correlation would indirectly express how much of the genetic value of the parents has been transferred to the offspring. It would still be quite a bad estimate because you don't really have a lot of information. How would you know which part came from the female, which part came from the male? So you would make a lot of assumptions, like it's a nice 50-50 ratio and so on. So, but anyhow, at least it would be possible to get a low reliability estimate of breeding values. Going on, you have to realize that this individual will also transfer its breeding value, its additive part, to its offspring. So basically, what is really important is that you make offspring individuals with multiple partners, test these in field trials, and then if you link this with the field trial performance of the parents, the individual itself, and all its offspring, you can get a reasonable estimate of what is the worth of this plant. But you see, this is costing effort, right? This is not just testing what you have and then continue with the best. You actually have to deliberately make these offspring trials, the offspring testing. And going one step further, you have to realize that these parents also pass on their breeding values to other offspring they might have, to nieces, nephews of that single plant. So what the basic idea of breeding value estimation is that you cannot estimate it over a small set of individuals. You estimate it breeding pool wide. You take all the individuals that you have in the breeding pool and you look at their pedigree. I'll come back to that. Look at their pedigree and then try to estimate for every individual in the breeding pool their breeding value. So it's not something you do on 1 or 2 plants or 1 or 2 trials. It's something that you do over your entire breeding pool. Now, the technicalities, I think this kind of models has appeared also yesterday during several talks. The machinery, again, not something that I invented. This is 1950s stuff, so it's not really hip. But this is linear mixed model analysis. I think we've seen a bit how it works. But what you're seeing here is a kind of a basic formulation. There is no one standard equation for breeding value estimation. This is what I would call a model framework. You can fit hundreds of models that will fit exactly in this equation, depending on how you define X, Z, how you define the variances of your residuals, the variances of your genetic parts, and so on. So there's no one straightforward way. This is just one representation of the general global way of formulating a linear mixed model. But it's up to you, or the quantitative geneticist, to find the most appropriate model in this structure. Now, what is quite crucial, however, is that you have some form of relationship matrix in there. Remember that I've shown that if we do it intuitively, that we're trying to track breeding values, how they transferred from parents to offspring, to their offspring, and so on. Now, to be able to do that on a breeding pool-wide scale, you need some similarity estimate between all the individuals. Now, traditionally, this relationship matrix is based on pedigree information. And that brings us to usually a quite sensitive topic. And I ask to the breeding company or the institute, so do you have pedigree information? How long does it go back? Because we want to see what the relationships are between the individuals. And the first answer is yes, we have everything. We have everything until, let's say, the 80s or the 70s. Great, great. So it all looks very promising. However, what I've noticed, then as soon as you start to dig into that pedigree information, that the consistency is often very low, meaning that individuals don't have a unique ID, which is something that Stephanie said, because they say it's related, like what is the origin of that individual? Probably something with individual X, Y, and Z. This is kind of the stuff that I'm getting at. That is impossible to analyze. So referring back to Stephanie's talk, pedigree information has to be maintained systematically, very accurately, and dating back many, many years. Just maintaining the pedigree for 1 or 2 generations will give you low reliability breeding values. So what is it that we need if we see this as a kind of a recipe for breeding value estimation? We need phenotypic performance data on both offspring and parents, and we need detailed pedigree information. It doesn't have to trace back to the 70s, but multiple generations. Now, if we look at the phenotypic performance data, usually breeding companies and breeding programs will use this kind of hierarchical approach So I've shown this also during the UCLAC meeting. You get this a yearly concept. So each year new trials are being laid out. And within 1 year you have what I'll call multi-environment trials, several trials which have multiple locations where the same individuals are tested. And these are the different locations. And within one of those locations that is nested within a multi-environment trial, that is nested within a certain year, you could have replications, depending on the trial design that you're using, and you could have spatial effects. So, at that point, it is up to you to try to find the best way to estimate genetic performance from this hierarchical, structured phenotypic data. Meaning that you can look at multi-environment trial, looking at the efficiency of your trial designs, looking at quantitative phenotyping, meaning compare that to just scoring something visually. I know from a pragmatic point of view that makes perfect sense, but often you will see that the information content of this subjective score is a whole lot lower than actually weights or lengths that are measured. So all of these things, balanced matings designs, for example, that means a lot of breeding programs make use of testers. They have a few guys out there for which they know they perform really well. So new material is crossed always with these testers just to be sure of what their performance is. That is not a balanced mating design. At that point, you'll get really good breeding values for those testers, but you don't really get an idea of what will this new line or this new candidate variety do when crossed with other individuals. So balanced mating designs, using multi-environment trials, using efficient trial designs, using quantitative phenotyping, using spatial analysis, and so on, will all improve the quality of the resulting breeding values. Pedigree is, in theory, very straightforward. Meaning that if you have just a list of individuals, in this case there are 7 individuals, it is very straightforward. We were forced to learn this, to do this by hand in our genetics courses. If you have the pedigree here, you have one individual that has 3 children that do some interfamily mating apparently. So a lot of inbreeding is going on here in this family. Then can you calculate the co-ancestry between each of these 7 individuals? Now this co-ancestry, this similarity matrix, is just basically every individual is either is on the rows and on the columns, and the similarity with an individual and itself is 1, and then the similarity between an individual and its offspring is 50%, because you get 50% of your genetic makeup from one of those parents, with the other percent it's also. So you basically get an iterative system allowing you to calculate the entire similarity matrix. Looking at individual 7, for example, you see that its relatedness with itself is higher than 1 because it's inbred. So you see that it's 1 plus 7 divided by 32, so not a very catchy number. But then anyhow, calculating this, what is called the numerator relationship matrix, is a standard thing to do. You don't have to do it by hand. There are software packages or R packages that will do this for you. So the only thing that this needs is a kind of list of who belongs to who has originated from which parents. And of course, there often the complication lies if you're confronted with a pedigree like this, that is not always that known. Which cross or which, like if you have synthetic populations, it's very hard to determine who was the original parent. So at that point, calculating this numerator relationship matrix becomes challenging, if not impossible. So just to say that quantitative theory as used by animal breeders is very nice, but for plant breeders, often things become more complex. Now, there's a solution for everything, but just to be aware of that it's not just straightforward adoption of the standard quantitative theory that will allow you to get breeding value estimate, except if you you're using pairwise crosses and so on, you're exactly in this scenario. So I've already shown this, the black line it is. So imagine that the black line is just testing and crossing the best, hoping for the best, looking for the per se performance. Then breeding value estimation, as you've noticed, will require some additional effort. But in almost all cases will result in a faster rate of genetic progress, and will therefore improve efficiency of your breeding program. But again, you will reach at a certain level, as soon as it's become a routine way of working, you will reach the plateau of this technology, if I can call it a technology. Here we go into the age of what I'll call marker-assisted selection. So what I've shown you so far, you don't need any molecular technique for breeding value estimation. Depending a bit on the pedigree thing, that might be a bit of an issue. But in the standard theory, you don't need any molecular information. So I think we've gone through this. What is a QTL study? What is a linkage mapping, GWAS study? And the last one is quite popular these days due to the availability of these high-density genotyping technologies. So the question now is, where do these fit in? How do we fit this in? Because if you remember, my statement was that you can fit all of this in the theory of quantitative genetics from the 1930s, 40s. So where does this fit in? Well, it really doesn't that much, in my point of view. Genomic selection, on the other hand, fits exactly into that framework. So genomic selection has been, I think, talked about several times. The idea is that we're going to estimate it, but look at the small difference I've put in here. Genomic selection, as presented, usually is used to say what is the performance of an individual, as a kind of a pre-screening technique, for example. We genotype an individual and then know what its performance is for certain key traits. In my point of view, you use breeding value estimation for that purpose, but mainly for getting prediction on its breeding values. Because as you've seen, breeding value estimation is hard. So if you have a model to predict the breeding value from the genotypic profile, whatever that may be, of your individual, then you can make accurate predictions of offspring performance even without that individual even being mature enough to make offsprings. So yes, you use it as a way of selecting the best, your top performers, but it's even more interesting to use it to find the best parents. And this is exactly what animal breeders do. This is why I put a cow there. Animal breeders will usually be using genomic prediction to find the best progenitors, to find the best parents, the guys with the highest breeding values for key traits, not to get the best cow or the best bull, because that doesn't really produce anything, right? Second thing that genomic selection will do for you, or in fact other technologies as well, is improving the accuracy of selection. So, as you notice, I'm always talking about now over breeding values. EBV is estimated breeding value. So, imagine that you would know the true breeding value. You never know, but this is a bit of a theoretical concept. So, this is your population. Every dot is an individual. And if you were to know the true breeding values and you put a cutoff here, then these are all the guys in red here and the green ones. These are your top performers. Imagine that you have a technology to estimate what are my top performers, like genomic selection. If your accuracy is only 10%, then you will miss out a lot of these guys, because you will identify all these guys as top performers, and only 10% of those will actually be top performers. So a low accuracy in recognizing breeding values, so low reliable breeding values, can have an adverse effect actually on your selection, because you'd be breeding with these guys here, the really low performers. So accuracy of selection is crucial in the entire breeding value scheme. So if you go from accuracy 0.1 to 0.7, so that just accuracy is like the Pearson correlation between your true breeding value and your estimated breeding value, you see that you go up to 40% of the winners. But you see that it's still quite a lot of probability that you will be selecting losers. So accuracy of selection is one of the key points where genomic selection, if we're talking breeding values, we're trying to predict breeding values for an individual, is where genomic selection can shine even over phenotypic performance of offspring, because those are, depending on the crop, usually very hard to obtain. Now, what are the possibilities of genomic selection? I'll go back to this. This is one of the topics of this afternoon. But I've said before that breeding value estimation, one of the limitations was that we can only predict the average, the mean of the offspring population. And that is unfortunate if you're in a case like this, where you have this one with low mean and huge variance, and then the red, so this is the inverse situation. Red is now superior mean, smaller variance, so the more likely choice. You can actually now, what is called here, cross-prediction by in silico generation of offspring populations. Sounds very fancy, but basically, if you have two parents, for which you know the genotype, let's say you've genotyped both parents with some high-density SNP chip or something, you have this high-density genotypic profile. You have a genetic map where these markers are laid, then you can make virtual offsprings of those crosses. Virtual offspring, meaning you will simulate crossing overs according to the distance on the genetic map of and you make offspring. Of course, if you make one or two offsprings, you know absolutely nothing. One will be here, one will be there. You will make thousands, if not tens of thousands, of virtual offsprings. It doesn't cost you anything. And you predict their trait performance. And you put these on a distribution. Does that mean that you will eventually get this guy? No, it just gives you an idea of the mean and the variance. So genomic selection is actually now a way to get both parameters of the normal distribution, mean and variance. So you know basically all there is to know about the offspring population. And then of course, multi-trait selection of parents, selection of seedling stage, early screening of segregating line if you're working in an inbred crop. While you're doing the different cycles of inbreeding, you can already start, for example, in F3, make a population of F4s, again, completely virtual, and look, what is the probability that I will get an F4 that will actually achieve something? So you can use these virtual offspring populations also while you're fixating lines. An ideotype creation, that's a bit harder. That is questioning what would the most ideal individual look like genotypically? What marker profile and how likely is it that we would be able to obtain it? Which crosses do we have to make to try to obtain or get as close as possible to the ideotype, to the ideal genotypic configuration? That's a real hard one, so that's not really a fixed methodology yet. However, in silico generation of offspring population is not something out of the blue. This is being used in practice in breeding companies as a standard way of selecting which crosses are we going to make. So again, genomic selection resets the bar, allowing you generally to improve again on top of breeding value estimation. Now, one thing that is what I see very often is companies or institutes saying, wow, that sounds great, we're going to do genomic selection. We have We are really strong in the genotyping part, so we have the field trials. So we're going from the black line, from per se performance traditional selection, selecting the best, hoping for the best. We'll jump directly towards genomic selection, because obvious, right? Why would you ever bother going to the next best thing? Now, unfortunately, it doesn't work that way, because what I've shown you with the phenotypic data analysis, all the things that you need to do, basically already bring you right here. You need advanced phenotypic data analysis for breeding value estimation. So jumping from here to here is basically just doing first this and then going to that. There is no way of skipping that step. So my advice is always, if you're right here now, why not look first at breeding value estimation and see where that brings you in terms of rate of genetic progress, so the beginning of my talk, the things that you can do. This is high throughput phenotyping. Is one of those things that is also now very advancing rapidly. You have people using drones, imaging, and so on. So how does this fit in this framework that I'm proposing here, right? The breeding value estimation. Well, technically, the images themselves, here you see a flower, you can judge if it's pretty or not, but imagine that the breeder is interested to know what is the potential of a flower to provide yellow offspring. Now, I've seen a lot of data sets in the ornamental breeding, and then they say this flower is yellow, and this one is yellow with little pink dots, and they describe it very accurately. Unfortunately, that really does not allow you to do any breeding value estimation. Now, digital imaging is a way, for example, this is a very straightforward approach where we just define a range of yellow pixels, for example. We define what is yellow. From this range and the spectrum to this, we'll consider that pixel yellow or not. And then do a principal component analysis of that image. So basically, now every dot here is an individual expressed in this principal component world. So I reduced a picture to a two-dimensional coordinate in this space. So this single picture now is one dot here. So another individual will have another dot. So what I've done here is actually quantifying from picture to a kind of estimate, like a score for yellow. If you would have done it manually, you'd have one variable saying it's a 7 on the yellow scale. This is a more like scientific approach, an objective way of measuring. Of course, I have 2 dimensions now. Sometimes, if you're really lucky, you can express a trait like a color in 1 dimension. Usually, it takes multiple dimensions. But the idea is that at this point, I have just phenotypic observations. And I can calculate breeding values for the components of this virtual yellow scale. So the message, what I'm trying to say here with this flower, is that digital imaging is just a way of phenotyping, and phenotypes are used for breeding value estimation. So again, digital imaging fits right into the same framework of breeding value estimation and so on. And you can then measure what the advantage is of using this versus your personal yellow scale from 1 to 9. So you can measure it. You can actually quantify how much did this imaging box that we bought and this camera, the 50,000 euro camera that we've spent here for making the picture of this flower, what did it bring us? So my advice is, again, quantify how much advantage you have from each introduction of a technology, like digital imaging, like drone flights. So, in general, if you're doing, looking at breeding data, I think most of you are then confronted with, because this sounds all nice in theory, right? So it's easy, we have images, we have pedigree data, we have marker data, so we'll just all integrate it, push the green button, and we know the results. However, like I said, pedigree data often, very often problematic. Look at consistency, meaning individuals. This is more the topic that Stephanie talked about. Consistency means that you have unique identifiers for every individual. Sounds trivial, right? So often am I confronted with individuals that are described as, this one is called Stephen, this is called Stephen in capital letters, this one is called Stephen_B, and all of these refer to the same individual. At that point, you don't have a consistent pedigree. Even more concerning are loops. Pedigrees, if you see them as a tree, should never contain loops. A loop is when you have an individual that is, let's say, this is individual Stephen, and these are its parents, and you go up on the pedigree, and all of a sudden, there is Stephen again. One of the great ancestors of Stephen is Stephen. That is a loop. That means that you cannot calculate this numerator relationship matrix, and that means that everything breaks down. So, consistency of pedigree information is quite important. The way of storing it, therefore, is crucial. Traditional phenotypic data is highly structured data, meaning, like I've shown, it's structured in years, in trials, locations, replications. That, I think, with a little bit of help, like the database technology that Stephanie showed, most people can harness. I'm not a big fan of Excel files, but as soon as it's something resembling of a database, you can make this consistent. But of course, it's crucial that the individuals that are here are also then in the pedigree, so it's all linked together. Molecular data, completely different ballpark all of a sudden. It's not highly structured, there's no hierarchies and there are no nested structures, but it's just massive. It's massive data volumes in dense matrix form. Like I've shown, digital images, again, massive volumes, but not in dense matrix form, binary data. From this binary data, you can do absolutely zero, so you have to have some feature extraction tools, like I've shown you with the flower. You have to try to convert it to something that resembles a phenotype. So you have metadata, when was this picture taken, from which genotype, and the extracted features, meaning the traits that you've extracted from the image. And then you have to store your analysis results, breeding values, cross-prediction, and so on. Add to that what I'll call breeding management, the logistics part of the entire structure, field trial designs, nursery organization, crossing designs, and so on. You see you have quite a bit on your plate as a breeder to get all of this data structured. Now, Stephanie showed you one example, which was right here, Oracle, of a database system. And most people, when talking about databases, they are talking about relational database systems. Relational means that generally the rows in your tables are identified by a unique key, and then these unique keys can be linked to one another in different tables. Like you have a pedigree table, where you have an individual with a certain key, and that key is the same as the individual or the germplasm table, which contains the definition of each individual. And then you have a trial table where the individuals, that same key is used to identify the accession in the trial. So these are basically a way of linking all kinds of tables using these unique keys, but Stephanie is way better at describing that. Now, that is a very mature and standard database mechanism, meaning I think it originates from the 70s. It has been by companies like Windows SQL Server and Oracle, I think, are the big players there in the commercial field. They've gotten this down. This works, this is stable, and this is highly reliable. But it is suited for hierarchically structured data, like trial data, like pedigree data, and so on, where we have these linked tables. Where it is less suited, if not to say unsuited, is if we're looking at, for example, marker data. You could say marker data is structured as well because you have a link to a genotype and you have a link to a marker definition, and together is a score. So that would be the most basic structure. But the biggest problem is the massive volume of marker data today. Before in microsatellite arrays or RFLP days, that wasn't the volume wasn't a big problem. Nowadays, we see that relational systems are not capable of handling these amounts of data. So there are different, what is called NoSQL-based systems. And there's, I think since the early 2000s, you have a massive growth of different ways of storing data that do no longer rely on the basis of the relational system. Key value is very simple. It's as simple as the word describes it itself. I have a key, like the identifier of my genotype, and a value, like its score. So it couldn't be more trivial. It's like you have a big bag of data where it contains a single piece of paper with a key, the identifier, and the value. So you could hardly call this a database at first glance, but the idea is here that you would have massive amounts of these data in there. That would be separated over different computers, over different hard drives, and so on. So these data would be distributed, would be mirrored to have several backups. If you're requesting a certain data point, he could ask it from this station or this server, and so on. So these are systems built for huge volumes of data, contrary to relational systems. Column families are kind of a compromise, document-based. So these are all graph-based. These are all different database mechanisms that try to find a solution for different types of data and different volumes of data. Now, if you look at, if we would have an optimal system, and we're looking at the data that breeders are confronted with, you'd have the relational system, so like the Oracle system, like Stephanie described, containing your phenotypic data, including pedigree information, logistic information, which crosses to make, and so on, nursery. All of these things fit nicely in a relational system. And that is, I think, also what is offered by most commercial plant breeding software, a relational system that allows you nicely to track all of your breeding. So that is very interesting. But what to do then with your molecular data? That would not fit in a relational system. If they try, they will fail. Many have tried, all of them have failed. So what would be the better solution is using some kind of wide column store. So that was one of the options I've shown there. But those wouldn't fit your images, which you still need to maintain as well. So you need a third system to keep your images, and then a distributed file system, meaning that your images are spread over different servers, would be the ideal solution. So if you look at that, you need this kind of very complicated setup as a breeder just to be able to store all the data if you're into those things. If you're just doing traditional phenotypic breeding, then this will do just nicely, right? It depends on the needs and the technologies you are adopting. So what Brno is actually offering here is a kind of a data warehouse that does exactly that. It allows you to maintain phenotypic observation, I'll call it molecular information, pedigree, image data, and what you're getting out of this is your original trial data, corrected or not, that depends on the analysis routines that you throw at it. Breeding values on itself don't have that much value. Cross predictions becomes more interesting. What are we going to do with these breeding values? What are we going to do with these genomic predictions? And then lastly, breeding advice, which is very closely related to cross predictions. So how does this look like? Well, it kind of looks different for each customer, meaning you have this central database system, and everybody can log in using something that has a decent browser on it. Internet Explorer is not a decent browser. And it's linked, either it's used as the original data source, like we do in the UCLEC project, where trials are directly entered by some form of Excel templates, trial data, pedigree information, and so on. But it can also just be linked with existing systems. Like imagine that you have a laboratory information management system, a LIMS system. Marker data is being generated and stored somewhere in that database system. If you want to use that, you would have to export it through Excel files and so on. Now you can make direct links between existing database systems. Companies or institutes that have existing phenotypic database system can link that system with the Brno system, meaning that this would be the data warehouse that contains all the information, either as the original data set, the original source, or as a kind of a copy of existing systems. But the idea is to centralize everything into one system. And this is a concept. At a certain point, all breeders have noticed that their results are dependent on time. Meaning, if you have an observation on a certain plant and you consider that your top performer, if you do another trial, you can get a really bad result, and all of a sudden it's no longer your top performer. So every moment of decision making is dependent on the data that is currently available. Tomorrow, if you enter new data, the situation could change. So Brno needed a way to kind of freeze the data to say, like, we're going to make a decision on which cross we're going to make, who are we going to select from the set of candidates. So that means you need to kind of wait to say, okay, this is the data that we're going to use, this is the analysis that we're going to perform on it, and this is the result. Tomorrow, if the original data changes, we'll have to redo the exercise. That's the idea. So that is called a processed data package. So imagine we start here with data synchronization. It doesn't say much, but it means you add new data. Is it from uploading an Excel file, or is it by you have an original database system and you feed something and it's synchronized with Brno, or the laboratory sends some genotypic score. Anyhow, new data arrives in the system. At that point, I will explain that later on, but you can calculate breeding values, genetic values, inbreeding coefficient, cross prediction. All of these calculations can be performed automatically or manual. I'll go back to that. But they're packaged into what is called a PDP. So basically, it's a kind of a set of, at this point, with the data that we had at exact that time date, these are the breeding values for all the traits that I'm interested. These are the genomic predictions. And these PDPs are then published, meaning made available to all the users of the system. So the word PDP will reappear several times. That's why I try to explain it here. So Brno offers a 3-lane data processing approach. So first, where it actually all started, the initial idea of Brno was having a completely autonomous analysis routine, meaning data would enter this. This needs, of course, a little bit of configuration. It's not like it's this smart that it will just look at your data and know which model to throw at it. So it takes a bit of configuration, but most breeding companies work with a similar way of trialing and all of this. So the system, after configuration, is able to estimate breeding values for all key traits. If you have genomic data, we'll try to train genomic prediction models, validate these. In other words, a completely autonomous workflow. If you're wondering, these Wi-Fi symbols, these represent autonomous driving vehicles, in case you didn't get the analogy. Secondly, is a visual analysis toolbox, meaning there are a set of functions allowing you to do basic graphics, calculate breeding values yourself, make genomic prediction models, validate them. These are all things that we're going to see this afternoon. And as most companies have dedicated statisticians, there is also a way to directly do everything in R. So you can extract data from the data warehouse directly from R, no need to import, export, you can do queries, and you can do your analysis. But again, you can wrap everything. Imagine that you have a team of statisticians, they can do their very advanced analysis, which are not possible in the autonomous routines, but wrap everything up and publish this as a PDP to the actual breeders. So that is the concept. Different ways depending on the level of expertise present in the institute or the company. I don't know how am I doing quite that bad. It's okay. So do I have to stop or do I go really fast? Doesn't it say? Well, it's really 3. But it's just basically repeating, so I can do both. I can show all slides and be fast. So the autonomous system, it tries to learn the different models, it re-estimates, it tries to detect outliers, which is not an easy thing in linear mixed modeling, and it tries to adapt. That means it tries to estimate variances of your breeding pool. Every selection that you do will change the heritability. So each round of analysis, variance parameters of all models are re-estimated. The analytics module, I probably won't be fast, I won't tell you much. This is something I can show you several things this afternoon. And the art thing, well, that is nearly impossible to demonstrate in a presentation. So that is something you'll just have to take my word for it. So, thank you.
Okay. Thank you. Thank you very much, Steven. I think we are all convinced of the interest. Who have question? David. Oh. Jan is running better than.
How does the when you're looking at the pedigree, when you're using an outbreeding crop where you may have many parents for individuals or populations, how does that affect the use of pedigree information?
Well, like I said, these are difficult situations if you don't know exactly what the parent is, because you've put together several candidates and you don't know who is the actual father. At that point, you have to rely on markers to calculate the similarity matrix, which is one of the topics of this afternoon. But basically, like I said, the quantitative theory is nice, but if you're working in kind of breeding scheme where you don't know the exact parents, yeah, then it kind of breaks down and you have to rely on marker technology.
Other questions?
So, Steven, I'm wondering, after your presentation, very, very good and useful, about, on your very first slide, you show the results from the maize breeding. In forage legumes, especially, I can talk about alpha of this improvement, about 10%, and halves go to agronomy and halves to the plant breeders, approximately. So in your equation from the very first slides, some of us are moving to hybrid or semi-hybrid breeding. So what about capital D? I know that can fit, but I would like to hear your comment about specific combining ability and all these things that you present. In terms of small number of parents in pedigree, in hybrids, even in alpha.
Well, I'll let you in a little secret about hybrid breeding. Most, if not all, hybrid breeders are selecting for high additive values. They're not selecting for specific combining ability. They're trying to do exactly the same, try to find lines that have better additive effects, and then crossing those. Of course, if some specific combining ability, the D component, then improves your performance of your offspring of your hybrid, then that's lucky. But if you want to do a systematic breeding, you'll use exactly the same approach, offspring testing and working on improving GCAs. So I don't know if that answers your question.
Other questions? Not at the moment? Yeah?
Steven, so I have a question that is related to this one and concerns also breeding of synthetics or of populations. Because you made the point that you are really estimating the value of a genotype as a progenitor. But in most of these, or in many of these breeding programs, the progenitors are not kept. So the clones are not maintained for very long. So do you see a way of circumventing, of avoiding or solving this problem by using some kind of how to say that? So, genetic distance estimation of the progeny that is used further in breeding, or is it totally absurd?
No, it's not totally absurd. It'll obviously be less efficient, but my guess is that you would still use pedigree information or breeding value estimation of parents who unfortunately no longer exist maybe, but you still, if you have to then select which offspring to keep, if you have the breeding values of the parents, I would select those offspring that originate from parents with high breeding values. Again, increasing your likelihood of having higher performers. Of course, it's indirect, therefore less efficient than actually using those parents to make the cross, but it would be the next best thing, I think.
Okay, so if there is no more question for this morning, I think we can stop here, have lunch, and we are back here in the room at 2 o'clock exactly, sharp. So thank you, Stephen, and see you very soon.